And there we go. Okay, I am, you can probably tell from the sound of me, I'm not at my best still. I don't know if my voice is going to make it till 6:30, so this could be an abbreviated class today. We'll see how far we get here. I had a few things that I wanted to cover. I graded your exams. Hopefully you saw your scores there. Y'all did pretty good. I was pretty impressed with the performance on the exams there. So nice job. Biggest mistake that most people may, a couple things I wanted to point out. On the question about where do residuals come from, that's a little bit more general than what most of you wrote. Most of you wrote things like, oh, it's from noise in the data, or inaccuracy, skin motion in the markers, or the fact that the markers and the forces are measured with different systems. You could eliminate all those things and you would still get large residuals on the model. Where the residuals come from primarily is from the fact that you're using a model. Like you're taking a simplified version of a person and telling it, I want you to apply these forces to yourself that I measured from a person and move in this way that I measured from a person. And it's technically impossible for a model to replicate that motion and those forces, because those motion and those forces didn't come from that model. They came from a person who's a lot more complicated than that model. So it's missing a lot of the degrees of freedom that had to be there in order to generate those data. And so you can technically never get zero residuals if you force it to produce exactly those forces and exactly those motions. It's an inevitable consequence of doing inverse dynamics. Basically, they're always there. You can clean up the data, you can add more degrees of freedom to the model, but unless the model is like a literal clone of the person, in which case it's no longer a model, it's just a copy, then you'll never get zero residuals. They'll always be there. So even if it's perfect data, it's less of a data driven thing and more of a model driven thing. And then what was the other thing I forgot to? Oh yeah, on the validation, a lot of you wrote about validating things like muscle forces or joint contact forces or things like that. Probably because I gave you that Hicks paper as a reference, and that's what that paper talked about. There I was more trying to get you to talk about the things that we've calculated so far. How would you go about validating those? And so let's just discuss that for a second. So suppose you use add biomechanics or whatever, and you calculate a knee joint angle, and you show it to me, and it's for walking, and I say, how do you know this is right? What would you do there? How would you check that? Or what could you do there?
Compare to previous literature.
Sure. That's probably the number one thing to do, is you calculate an angle or a torque, or you measure a ground reaction force or whatever. Go to the literature and find some highly cited papers, hopefully highly cited because they're good papers, not because they get cited because they're stupid or something. But find some like well-known papers that studied a similar motion in a similar population, and let's give them the benefit of the doubt that they technically did this correctly, and compare your angles to them. Do they look approximately similar? Do they have torques or whatever that are approximately similar? So that's a good thing to do when you calculate output, to compare it to similar reports in the literature. Are you getting similar results there? Now, typically you'll be a part of your study that's a little bit novel and a little bit new, so there won't usually be like a direct copy of it that you can try to replicate in the literature, but there should be some condition that you can check that might show, okay, this is probably a good check that technically I'm doing this correctly. Okay, second thing I wanted to cover before we get into the new stuff for today is I posted homework number 3, and let me pull that up here. There it is. So this one will build on what we covered most recently on making changes to the model. And so this one asks you to basically repeat what you did in homework 1, but just the kinematics. So you don't have to do the inverse dynamics. So you just doing the kinematic analysis in add biomechanics, and do this 3 times. Okay, just repeat it by default with tracking all the markers in the model in the walking motion. That's the first part. Second part is do that same thing as the first part, but have it not track the upper body markers, have it just track the pelvis and lower body markers. And the best way to do that, oh, my dog heard funny noises and came exploring to see what's going on up here. The best way to do that, and I gave you a tip down here, is add biomechanics if it doesn't find consistency between the names of the marker data that you're giving it and the names of the markers in the model, it just won't try to track that marker. Okay, so the best way to get it to not track something is I just go into the name of the marker in the model and just put like an X in front of it. You know, like if I don't want it to track the left acromion marker, I go in and just put an X in front of the name of that marker, and then it will not be able to track that marker because there's no marker with that name in the data. And so make a version of the model that has all those markers renamed to some name that's not actually in the data, and then repeat the tracking. You should see that it'll track the pelvis and lower body markers still pretty well, but the upper body motion will just be this really like, you know, weird rigid motion. It won't move those joints at all because it's not, you know, tracking them away from the default pose at all. And then the third one, and this is the hard part and the part that builds on what we did recently in class, is now repeat the first condition again, tracking all the markers, but take the model and modify it to allow the shoulder joints to not just rotate in 3 dimensions, but to also translate in 3 dimensions. Okay, so basically give the shoulders each 6 degrees of freedom. Okay. Now to do that, here's my model, right? This is my Rajagopal model. The shoulder joints, it calls those down here under its joint set, it calls those acromial joints. That's the right shoulder there. And you can see, so it's the joint between the torso and the right humerus. And you can see there, it's got 3 coordinates defined: arm flexion, arm adduction, arm rotation. Okay, so that would be arm flexion, arm adduction, arm rotation. Okay, those 3 motions. You'll need to define 3 new coordinates, so bringing it to 6 total of XYZ translation of that joint in that socket. Okay, you can name them whatever you want. I'd just call it, you know, arm X, arm Y, arm Z, or something like that. Okay. But then that's not the end, right? You have to go down here and then define in the spatial transform, you've got those 3 rotations defined, right? So there's a rotation linked to the arm flexion coordinate, the arm adduction coordinate, and the arm rotation coordinate. Under these 3 translations, they don't have any function defined there, right? So you need to define probably these linear functions up here for the rotations, also define them down here for the translations, and then link those translations to those 3 new coordinates that you define up there. Okay, so giving those shoulders the existing 3 rotations and the existing 3 translations, and see if that improves or affects the tracking of the markers. Okay, I haven't actually checked this, so I think it's going to make it better. I'm not sure it's going to make it better, but it's again an exercise in learning to modify the model, not so much an exercise in necessarily making the quality of the tracking better. Okay, then I asked you to simply report the IK tracking errors. Did making either of these 2 changes meaningfully improve, you know, how well the model was able to track the markers? And then make a graph of the knee flexion angle for each one of those 3 cases, and whether or not it improved the tracking at all. Did that overall have a meaningful effect on the shape of that waveform that you got for knee flexion? Okay, so that PDF or that prompt is posted on Canvas. I know I just introduced that, you know, 5 minutes ago, but any immediate questions anybody has on that, any of those tasks? Should be fairly straightforward.
All right, so if I understood right, it's normal simulation with no upper body tracking, and simulation with upper body tracking and more degrees of freedom in the shoulder. And then our output to compare is the knee angle.
And the overall tracking error. That big number it pops up at the top of add biomechanics where it says a certain number of centimeters. That's the main output, and then the knee angle, the secondary one. Yep.
Thank you.
Could you say how the tracking error is calculated? Did we go over this already? Like, what is the tracking error, basically?
Have you run anything in add biomechanics yet, Rana?
Yes, so it's one of the outputs you just mentioned, but
Yeah.
in
Let me
terms
see
of
if
how it calculates it.
yeah,
did
let
we
me
go
just
over it?
see if I have one here. I should have a finished one.
Like, is it a measure of the quality of tracking?
Yeah, in general.
Okay.
Let me just pull it up so I'm clear that we're talking about the same thing. Give me 1 second here. And one of these should be processed. This one. This website's kind of pokey sometimes. Yeah, so you're talking about like this number up here. Where did that come from? It is, so to answer that, let me go to OpenSim. Try this one. No, that's my one with my funny looking head. Let's not use that one. How about this one? That'll work. Okay, let me just get an IK started here. I don't seem to have an IK set up. Let me just start one, I guess. Okay, this won't be a good result, but I'll just show it here. Okay, so down there on the messages screen there, for each frame, it's showing you like a bunch of outputs of its calculations and optimization for that frame. It says total squared error, which is the thing it's trying to minimize when it's, picking how it moves. Marker error RMS is the root mean squared error, and max is the largest single marker error. Marker error RMS here, to my understanding, is like there's 63 markers on this model, and for that particular frame, it's taking the positions on the model of all 63 of those markers and the position in the data of all 63 of those markers and calculating the RMS of those. So the root means, do you guys know that term, RMS, root mean squared? Some of you probably do, some of you don't. You take all the errors, you square them, you average them, you take the square root of that. That's the root mean square. So you can think of it as like the average deviation of the markers from the data. And it has one of those for each frame here. And so if you average that RMS over all the frames, that I'm pretty sure is this number up here that Add Biomechanics is reporting. So it's the average of it's the RMS of each frame averaged over time, averaged over all the markers, if that makes sense. So like if you just guessed like what on average is the deviation from the model and the markers, on average, it would be 2.29 centimeters at any particular frame for any particular marker. That's kind of what that's saying. Okay, other questions before we move on? Chioma, you joined late. Sorry, I was introducing homework 3. I'm recording this lecture, so I'll post it at the end of class today. You can see the part that you missed, but I was just introducing homework 3, and then what we do there, it involves making some changes to the joints of the model and running the kinematics a few times.
All right, thank you.
Yep. Okay, we are going to shift gears a little bit for the rest of the course this semester and do a little bit, actually a lot less inverse dynamics and some more forward dynamics. Anybody ever done forward dynamics? Anybody know what forward dynamics is?
In robotics, I've done it.
Okay, yeah, that counts. Biomechanics, like most things in biomechanics, we stole our methods from robotics, so that's where forward dynamics came from. So it sounds like it's kind of the opposite of inverse dynamics, right? Inverse, forward. In inverse dynamics, we take a measured motion and we compute the kinetics that, according to laws of physics, must have been there to cause that motion. So think about it like, I've got my model here and it's moving, and I measure that motion. And if I assume I've measured and registered it accurately, and I know the physics of this model, I can calculate kinetically what had to be happening to cause that motion. Forward dynamics is the other way around. Rather than starting with the motion and calculating what caused the motion, we start with what caused the motion and calculate the motion that results from those kinetics, right? So the simplest way of thinking about it is take this model here and apply certain prescribed torques to its joints. How is it going to move, or how will it move in response to those torques? So you can even think simpler than that, right? Here's my phone. If I let go of it, what's going to happen? Well, it's going to fall, right? Because gravity is acting on it to pull it downward, right? So in response to that applied force, it's moving in a certain way. Forward dynamics is that process, but using the physics of the model to calculate the motion. So you apply certain forces to it, and then according to laws of physics, how does it move in response to those forces? And then typically doing simulations like that involves kind of an iterative process, because suppose, and forget about like muscles, let's just keep this real simple and talk about like net torques at joints. Suppose I wanted to get my model here to walk like a human, right? It would be really unlikely that I could just come up on a random guess or even educated guess at like, what is the time series of torques I should apply there that will get it to do that, right? I'd probably guess, and maybe it, stumbles forward a little bit and then falls on its face. And then I'd go back and refine it a little bit, and maybe it walks a little better. And then I go back and keep refining it and keep adjusting those torques until I get it to do what I think is a nice kind of good looking walking motion. Typically we won't have like a good intuitive result like that, where I can just apply on a guess or from a measurement some actuation to a model to get it to move or walk like a real human. Typically it involves some sort of optimization procedure. And if you hear stories about like, oh, forward dynamics, it's really slow, it takes a long time. It is really slow, and it does take a long time compared to inverse dynamics. And the need to do that optimization is why you're essentially solving the problem many hundreds of times or many thousands of times, essentially trying lots of different guesses for what forces to apply to the model to get it to do what you're trying to get it to do. So let's start with a little bit of history in terms of where this business came from. The common applications that you will see here in biomechanics for doing these forward dynamic simulations are a specific, specific type of simulation called an optimal control simulation. And that's a fancy word for basically what I just spent the last few minutes describing, where I have this model and I give it some goal that I want it to move in a way best achieves that goal. Okay. That goal could be something related to like performance, like it might be jump as high as possible, right? Raise the center of mass up as high in the air as you can. Or maybe I want to simulate sprinting and I say move, translate forward as fast as you can. Maybe I give it some target time series of motion that I want it to try to track as close as possible, right? Or maybe I give it some kind of broader motor control type goal, like move from here to here with minimum energy expenditure, minimum muscular effort, or something like that. So some quantifiable goal that I can, from the state of the model, calculate and attach a number to how well it achieved that goal. Then I want to figure out, okay, what are the forces in terms of like torques at the joints, or forces in individual muscles, or control signals to the muscles that result in muscle forces, however you want to think about moving the model or controlling the model. What are the optimal signals that I input to the model to get it to achieve that goal as best as possible, right? To get it to jump as high as it's able to, or sprint as fast as possible, or to track that target motion with the best possible accuracy. Okay. So that's an optimal control problem in a nutshell. Figure out how to control the model in the way that best achieves some quantifiable value of the state of the movement, or the quality of the movement that it's performing. Okay. That quality, or that goal, will be reflected in what you, the user, specify as the cost function is the term that you'll hear, or the objective function, and that'll be something like jump height, or sprinting speed, or metabolic cost, or tracking error, the deviation of the model's joint angles from some target joint angle, something like that. Okay. Where all that business came from had nothing to do with human movement, and a lot to do with less peaceful applications. This was born out of the international relations in the 1950s and 1960s. Does anyone know what was kind of the main, who were the two main like global rivals on planet Earth in the 1950s, 1960s, like the immediate post-World War II era? What was, who were the main, forces in the world button heads at that time?
Cold War, are you talking about
Cold
that?
War, right?
Yeah,
United
so
States
Russia, and
the
Soviet
Russia at the
Union,
time.
yeah.
Yep. At that time, we had learned in World War II that nuclear weapons were really powerful, and were also really an existential threat to human existence. And so we kind of fortunately learned as a society, okay, we don't want to actually use these. We just want to represent the threat of using these. And that's where the Cold War came from. And so it resulted in the United States and the Soviet Union building progressively bigger and more powerful nuclear weapons, and stockpiling more and more nuclear weapons as an arms race, like a deterrent to either one to actually attack the other one, because if we fire all our stuff at them and they fire all their stuff at us, then we both lose, right? But the technology that went into developing those weapons and using those weapons led to a lot of optimal control methods, right? So let's see an example here. And I'll need to share my screen 1 second here. So you should all hopefully see my drawing program here. Everybody see my blank white page there? Okay, cool. And if I did this right, I should be able to draw on the thing with sketches. Add sketch. I don't want to use my iPad, I want to use my phone. Insert from, there we go, Ross's phone, sketch. Okay. This is kind of cool. It lets me like draw my finger on my phone, and then it copies it to the screen here. But suppose, and I'm not a very good artist, this is supposed to look like a rocket. Okay, you have a rocket down here, right? And you have some target here that you want to try to hit, right? And you want to be able to get your rocket to the target in minimum time, right? Because that gives the target the shortest amount of opportunity to get out of the way or respond and fire a rocket back at you. So we might want to figure out, what direction should I point this thing, and how much thrust should I give it in order to get from this position to that position as quickly as possible, right? So I'm optimizing the control of the rocket, or the modifiable parameters of the rocket, in order to minimize the time that it takes to get from this position up to this position, right? Now, it's also a little more complicated than that, because the best way to give the rocket a lot of thrust, right, a lot of power, is to give it a lot of fuel. But that makes the rocket heavy, and that makes the rocket expensive. And it's kind of this circular problem where the heavier it is, the more fuel it has to get a lot of thrust, but the more thrust you need to overcome the weight of all the fuel there. And so you might also have this competing objective where you want to travel to the target in minimum time, but using minimum fuel, right? And so then your cost function, or your objective, might be something like time taken to get to target plus amount of fuel used, right? But then these are different units, right? This is probably a time in, if I'm shooting a rocket at a target, probably minutes, right? And amount of fuel, that's probably in liters or gallons, right? And so maybe I want to attach, a different weighting constant here, a different weight here to the amount of fuel used. And I could increase that to some large number to really prioritize, okay, I really don't want you to use a lot of fuel. I want you to do this economically. Or maybe I really don't care about how much fuel is used. I just really want to hit that target fast. So I give that a small weight, right? So this is a good example of a basic optimal control problem. And all the research that was done there also led to more useful, kind of still war-related applications, but also more peaceful and interesting scientific endeavors in terms of the space race, right? This was also the era in human history when we had developed technology that was able to travel into outer space with without humans, but also with humans, like in the space shuttles and in the rockets and things like that. So the moon landing, and so that's kind of a similar idea, right? Now consider my rocket not being a missile or a weapon, but now consider my rocket as a space shuttle. And now consider my target is not an enemy that I want to hit, but it's a moon or a planet that I want to get to. And kind of here, the same idea applies, right? I want to blast off my rocket, and I want it to travel along a certain path. And I want it to probably take the minimum amount of time, right? Because humans aren't very good at surviving in outer space or in environments other than planet Earth. So we'd like to minimize the amount of time we have to spend up in space or stuck in this spaceship. But I'd also like to minimize the amount of fuel that it takes to get there. That makes my rocket lighter. There I can put in more surplus fuel in case I need to make adjustments and I'm stuck in outer space millions of miles from home. And so kind of a similar idea here, right? Where I may have these two possibly competing objectives and I need to decide on a weight between them. But just the more general idea of controlling the system in the way that best achieves some objective here. Okay. So that is optimal control in a nutshell. And now take that and extend that up into controlling the human body, right? And you can see this in a surprisingly large number of cases in human movement, where we tend to, whether we know it or not, move in ways that are optimal according to some subconscious thing that we're trying to minimize or that we're trying to control, right? Like the example that I use in my undergrad class on the first day is, and this is in like a big lecture hall with 100+ people or so, is I'll tell everyone to stand up, and then everyone stands up. You gotta be careful I don't bonk the ceiling here. And then I'll tell everyone, okay, stand up again, but this time pay attention to what's the first movement that you do. And the first thing everybody does is you lean your trunk forward, right? And then I'll tell everyone, okay, stand up again, but this time skip that first movement. Don't lean your trunk forward. And maybe some of you have, the leg strength to do that, but I can't do that, right? I can't stand up without leaning my trunk forward. Yeah. And so whether we know it or not, we're moving in, you're not consciously thinking, oh, I got to lean my trunk forward because that makes this easy. But we're moving in the way that is minimum effort by some definition. Maybe it's minimum joint torques, maybe it's minimum muscle excitations, maybe it's minimum metabolic cost, but we're moving in the way that minimizes the amount of effort it takes to perform that particular task. So optimal control simulations are just quantitatively formalizing that in simulations. Rise up from this chair, move from this posture to this posture and do it with minimum joint torques, or minimum muscle excitations or minimum metabolic energy expenditure or something similar to that. So any questions so far on just this largely theoretical introduction here on optimal control simulations before we actually see it done? Okay, in times of yore, and that was back in 2006 to 2010 when I was a grad student, there were maybe like 5 labs in the world that you could go to learn how to do these types of simulations, because they were just really not hard, but just like required really specialized like expertise and training, and there just weren't that many people in the field who had that training. Most of them stemmed from like a fella at Stanford who was named Felix Zajac, who was an expert in it. And then he had a few grad students who kind of proliferated it to a few other labs around the country, and everybody kind of came from that small tree there. But it used to be something that not a lot of people had the training to actually do. There's since been some developments in software that allows you to do these simulations a lot more easily and a lot more quickly, and gives you the convenience of using OpenSim models, which I can't overstate what a luxury that is to be able to do those kind of simulations with OpenSim models. It really makes things a lot easier and a lot quicker on the side of the user. So let's take a look at an example of actually doing this in MATLAB and using OpenSim's optimal control software, which is called OpenSim Moco, M-O-C-O. If you have a fairly fast, fairly new computer, I'd recommend running this along with me here. If your computer is not fairly fast and not fairly recent, I wouldn't run these codes on it. I can show you how to stop it if you start it up and it's just chugging along and taking forever. But on my like fairly new like Apple Silicon laptop here, which isn't even a particularly powerful laptop, this will take like a minute to run. It's something that if you have an older computer, it could take many hours to actually finish on it. And the actual like research grade, like fully 3-dimensional, complex simulations that I run recently for like the amputees and stuff, those are simulations that run for a day, sometimes 2, sometimes 3 days straight before they actually finish and converge on a good solution. So be aware here that these can be time-consuming simulations. The examples should be pretty fast, but even on like an old computer, the examples may not necessarily be fast. So if you have OpenSim installed on your computer, where can you find this? On mine, if I go to my documents, oh, you guys can't see that. Sorry, let me share my screen. On mine here, if I go to my documents and I go to OpenSim, and 4.4 is my install. And then if I go to code, and then MATLAB, all this stuff runs in Python too. If you're a Python user, you can check out the Python there. I don't know much about Python, so I stick with MATLAB, but Moco also works just fine in Python. So MATLAB, and then Moco. And in here is a bunch of examples of doing kind of basic things in Moco. We're going to start with the simplest one here, which is this example 2D walking. And then let's open that up in Moco. They have 3 different examples here. There's example 2D walking, and that's the one we'll start with. There's example 2D walking metabolics, which includes a part in it that calculates the metabolic energy expenditure of the muscles and then tacks that on to the cost function. And then this third one here I haven't done a lot with, but this is one related to generating simulations of like asymmetric strides and simulations of gaits that are not symmetric. That one I haven't looked too much at. But let's start with the simplest one here, example 2D walking.m. So open that up in MATLAB. Okay. Now, before you run this, there's a couple changes that you want to make to the code. Scroll down a little bit here. And on line 204, by default, that line is probably commented out like that. and you want to undo that comment and have it say in the code there on line 204 that study.visualize command. Okay. And then most importantly, down here on line 223, that return command is probably commented out, and you want to undo that comment and get it to actually execute that return command. This one's particularly important because this code actually does two simulations. It does what's called a tracking simulation, which I'll explain that in a little bit. And then after that, it does what's called a predictive simulation, which I'll explain again what that is in a little bit. The tracking simulation is fairly fast. The predictive simulation is not fast, even on my fairly fast laptop computer here. So we want it to stop after doing that first fast tracking simulation. Then we'll skip the predictive simulation for now. Okay. So make those two changes. And then run the code. And we can observe what's going on here. And let's just have it finish, and then I'll explain what it was doing when it finishes here. When I was learning how to use Moco during the pandemic, this is what I would watch while I was like exercising on my bike trainer. I would prop up my laptop here and watch the output from Moco and see if it was going to converge soon. I forget how long this takes. I haven't run it in a while, but it should be done in a couple minutes at the most. Oh, there we go. Okay. And then it makes this little animation here. Not the prettiest looking walking gate in the world, but a walking gate nonetheless. To get out of here, you can move this visualizer around and take a look at it. To stop this visualization, you click on this window and push the escape key on your keyboard, and that'll stop it. And that'll bring you back to your active MATLAB window here. So what was going on there? This code here is taking an OpenSim model, and it's this particular model here, this 2D gate.osim. And if we open that up in text editor, we can see it's got some things here that are different from what we've got in our own model that we've been working with, but it's largely the same type of model that we've been working with. Like it's got muscles and it's got all the usual things defined, like path points and max isometric forces and whatnot. And if I keep going down here, it's got like bodies and things like that all defined. So it's got a femur and joints and all the usual things. So it's taking that model and it's saying, here are these reference coordinates, which is data from somewhere for the angle of pelvic tilt, the pelvis horizontal translation, the pelvis vertical translation, left hip flexion, right hip flexion, left knee flexion, right knee flexion, ankle angle, yeah, all of the motion, some target motion of the angles of the joints and the segments that I want the model to try to track as closely as possible. And it's also giving it some reference ground reaction forces. So horizontal ground reaction force for the right foot, horizontal for the left foot, sorry, vertical for the right foot. And you can see the same stuff there for the left foot. So it's giving it a set of target motions of the model's joints and a set of target ground reaction forces. And it's saying, if I go back to my picture, take this model and find the time varying excitations that are sent to these muscles that produce the forces in those muscles that cause the model to move in a way that tracks these target forces and these target motions as closely as possible. Okay. Now, it's a little bit more complicated than that in practice. There's actually 3 terms in this model's cost function. There's the motion tracking error. There's the force tracking error. And there's I'm going to call this muscular effort. Okay. And that muscular effort term, why is that important? Let's just see an example there of why that's important. You can see here that while this model is moving, even in the middle of the stance phase of the right leg there, the muscles are not very active. This model is coded up here such that like the shade of the color of the muscle shifts from like blue to red, depending on how active it is. And you can see here that even when it's in the middle of its stance phase, the muscles are not, super highly active. And that's kind of what we would expect for walking, right? Walking doesn't really, at least under normal healthy circumstances, doesn't tax our muscles that heavily, right? So we wouldn't expect like all these muscles to be, all shot with red here, max activations of all these muscles. That is because there's a term added here in this cost function that says muscular effort, right? So what this is minimizing is it's taking all of the model's joint motions, say the angle of the knee in the model, the angle of the hip in the model, the angle of the pelvis, all those motions in the model, comparing them to the target motions in the data, taking all those differences, squaring them, and averaging them. Okay. Then it's doing the same thing for the ground reaction forces. It's taking the model's ground reaction forces, comparing them to the target ground reaction forces, taking the difference, squaring them, and averaging them. And that's the ground reaction force tracking error. Okay. Then it's taking all the time-varying muscle excitations that the model used to move in that particular way, squaring them and adding them all up, right? So that's the quantity of muscular effort there, the sum of the squared excitation signals of the muscles. Okay. So that's why it's tracking this motion with relatively little muscular effort, because there's a term there in the cost function encouraging it to use minimal muscular effort to perform this tracking well. And generally there will be a trade-off. Like generally these things will be in conflict with each other. Like if I zero out muscular effort and force tracking, I can probably get the model to track the motion perfectly or nearly perfectly, right? So within like, a sub degree accuracy, right? But it won't necessarily do that with realistic forces, and it'll probably use an unrealistically high amount of muscular effort to do that, right? So then I tack on ground reaction forces. I want you to track those too. And I tack on muscular effort. I want you to use a realistic amount of your available muscular effort, or your capacity of producing muscle forces to do this. And then again, this is where that weighting comes into play. Let's call that 2. And this is kind of the hard part of doing these type of simulations. And it's again where a lot of the art of computer modeling and less of the science of computer modeling comes into play. Where if you go back to the top of this code here, you see here that it's got a control effort weight, state tracking weight, and a GRF tracking weight. The GRF tracking weight is self-explanatory, right? That's the weight it's placing on the cost function on ground reaction force tracking. State tracking is the weight that it's placing on tracking the target motion. And then control effort is the weight that it's placing on the muscular effort, on the muscular excitations. Okay, so that would be saying, if I go back to my cost function here, the motion error gets a weight of 1, force error gets a weight of 1, muscular effort gets a weight of 10. Why those values, right? Why not, 2 and 6 and 37, you know, like where did the 2 and where did the 1 and the 1 and the 10 come from? This is just a demonstration, like this is just an example code to start with. Typically here, what I'll do is I'll start one of these just at 1, right? Like just arbitrarily set the motion tracking error equal to 1, right? And then I'll try to come up with a force tracking error that also gets it to kind of track the ground reaction forces with reasonably similar accuracy compared to how well it's able to track this motion here, right? So that's going to be kind of an iterative process. Like maybe I start off making this as 1, and I realize, okay, that's placing way too much emphasis on tracking the ground reaction force. So then I try it again and I make it 0.1. And I say, okay, that got pretty good. That's close enough. But it did it with way too much muscular effort, right? So then I go to here and I say, okay, maybe I want to make that 100 or 25, you know, and so it's this kind of like organic, like iterative process that a lot of people find a little unsatisfactory, but it's not something that really has a lot of clear-cut, like objective ways for picking what those particular values are. But that is optimal control simulations in a nutshell. You come up with a model and you come up with a goal that you want that model to achieve. And sometimes that goal is easy, right? Like if this was a jumping simulation, my objective would just be maximum height, right? So I'd have the model calculate like what's the peak height that the pelvis or whatever got to, and then that's just the only thing that's involved in jumping there, right? But sometimes for something like walking, it's a little bit more complicated. Now, I mentioned this notion of, oops, come back. This notion of tracking simulations and predictive simulations. And you'll see those two terms a lot in this literature, in the optimal control simulation literature. You'll see simulations typically described as being tracking simulations or described as being predictive simulations. That comes down to the form of this cost function. A tracking simulation is typically one where you have some target motion, typically movements and ground reaction forces, specified from data, from measurements in human participants. And you're trying to get the model to move like that measured data as close as you can, and with this cost function here. And then maybe on top of that, you also have some effort-related term tacked on there. Okay. A predictive simulation has just that muscular effort term. So think about it as like setting literally 0 weight to that tracking. And so that would just say, move in whatever way you can that minimizes the amount of muscular effort, regardless of how closely you track this target data, this target motion, and regardless of how closely you track these target forces, right? And so that's a predictive simulation. Predictive simulations are typically useful in like more motor control type applications. Like I could come up with lots of different potential criteria here that I think the nervous system might care about when it's generating a movement like walking or running, right? And so I might try lots of different candidate cost functions there and see which one produces the movement that compares most accurately to these, you know, real data from real humans, without telling the model to explicitly try to track that data as close as it can, right? So that'd be a typical application of predictive simulations. Or like a jumping height simulation would be an example of a predictive simulation. It's not telling the model, hey, here's this target motion of humans jumping, try to track it as close as you can. It's saying, hey, model, jump as high as you can. And then you typically want to compare what it did to what humans do when we try to jump as high as possible, right? So those are those two different types of simulations you will see in the literature, described as tracking simulations that attempt to track a measured human motion, and predictive simulations that are trying to minimize or maximize some index of performance, regardless of how well it compares to human experimental data.
I have a question
Yeah, sure.
about the predictive simulations that
Yep.
you want to tell it like jump as high as you can. What does it make it an optimal? Because optimal is when two things go the opposite direction and you find something that satisfies both of them in the best way, like tracking error and muscular effort. But if you just want it to like jump as high as it can, so it will activate all of the muscles and make a high jump. What prevents it from using that maximized muscular effect?
Nothing in that particular case. This gets into some of the more esoteric elements of optimal control. It doesn't necessarily have to be a trade-off between two competing objectives. Picture like you have, my y-axis here is jump height, and then my other two axes here are the variables that I can manipulate to affect the jump height. And I'd be looking in that solution space for the combination of those two variables that gets the highest value for the jump height. And there's lots of different ways that you can do that. You can just repeatedly guess randomly and take the one that gets the best result. You can start at some hopefully good initial guess, and then you'll get better and better and better and better and better. Oh, now no matter what direction I move, I get worse, and so now that's my optimal solution. But it doesn't necessarily have to be two competing objectives that are being balanced out there. Often for like simulating submaximal motions, that will be the case. Like for walking, for example, like what's the best way to move forward with minimum energy expenditure, right? It's not to walk, it's just to face plant, right? But you'll often have a motion that you're trying to track to say, okay, you have to try to move roughly like this, but do it with minimum energy expenditure. Or you'd give it a constraint that said you have to translate at least this far in this amount, specifying like a speed constraint, like move from here to here in this amount of time with minimum energy expenditure. Or you have to stop and start, with periodic motions. Like you can't start like this and stop like that. You have to start like this and end like this. So there'll be constraints that you'll tack on there that kind of restrict the solution domain a little bit. But it doesn't necessarily have to be two competing terms in the cost function. It can be just a single term, like maximize this one thing or minimize this one other thing.
Thank you.
Yeah. Other questions? Okay, let's take a break until 5:05 and let me get my voice back a little bit, and then we will take a little bit closer look at some of the features of this model and the features of the code here. I guess I could have paused the recording. Oh well. It's gonna have this weird like 10-minute dead space in it. I'm always nervous to pause because I don't know if it's gonna start again. And okay, let's talk a little more about the form of this cost function first. Let me share my screen. Okay, let's make that a little big. So you've got your cost function, right? And let's just first think of it as like the motion tracking error plus GRF tracking error plus muscle effort or something like that. In this motion tracking error, you can think of that as essentially being model knee angle minus data knee. Maybe you square that plus model hip minus data hip. Maybe you square that, you know, think of something like that for all of the variables that you're tracking in the data compared to the model. Something, and you can also think of your ground reaction force as being like that, right? Model GRF X minus data GRF X squared plus, you know, all three of those components. And you got to come up with a weight on each one of those, right? What I've had good results with in the past and how I still like to do it is to weight these variables based on their standard deviations in experimental data, right? And the idea there is that if the standard deviation is really small, then that's data that's really unvariable and really consistent. And so I want you to track that variable really well, right? So for my weight on the knee there, I might make that, you know, 1 divided by the standard deviation in the data for the knee, right? And then for the hip, I might make that, you know, 1 divided by the standard deviation for the hip, right? And then actually probably I square that because it's squared over here too. That's nice because it gives you like a good objective way of coming up with the weights, at least on these two terms. And it also is an easy argument to make on why you picked it. You know, and let me show you an example of a result that produced. This is my all-time favorite paper that I've done in my own work. This was our first simulation that we did of walking with prosthetic limbs. And there we generated simulations like I've been talking about, trying to get models with and without prosthetic limbs to track, you know, able-bodied human experimental data. And we weighted all the different angles and ground reaction forces proportionate to the standard deviations in the experimental data like that. And I like that because it says, you know, here, like in the middle of the stance phase for the horizontal ground reaction force, where that standard deviation is really small, I want you to track that mean value really close. But then up like here, for example, like the peak knee flexion angle in the swing phase, it would place relatively less weight on tracking that because that's a really large standard deviation. So you can deviate from the mean value by quite a bit and still be within, you know, a fairly reasonable statistical range of like a normal value for those data, right? So it's basically saying when you weight those tracking variables inversely proportional to their standard deviation like this, it's basically defining, you know, like these shaded out gray bands here and saying, you know, try to get the movement, try to get it within those bands, you know, try to get it close, you know, to be kind of statistically close to average human experimental data. But if that band is really wide, you know, just get it kind of close. If that band is really narrow, get it real close, because I know that's real consistent. It's something that doesn't vary a lot from person to person. So that's something that I recommend doing for tracking problems. It's a nice objective way of defining those tracking weights, and tends to produce good results. You still then have to come up with the weight on this other term there, but that's where having, say if it's a walking simulation, that's where looking at like the model's metabolic cost can come in, right? Because maybe you weight these variables according to their standard deviations, and then you got to pick this one here, this W3, what should that be? Well, maybe that one you keep these weights here, and then you adjust this one to get a value for that produces an overall metabolic cost of walking that's realistic, for example. So you don't have to just kind of take a shot in the dark at what these can be. There are, fairly good objective ways of coming up with values for them. Okay, let's take a little bit closer look first at the model that we are using, and then at the code that is generating simulations with that model. The model here is this 2dgate.osim. And if you look through it, you should basically see things that are all pretty recognizable from the model that we've been using in class. This is a much simpler model. It's a two-dimensional model. It has fewer degrees of freedom, fewer muscles, but you should see a structure of it that's fairly recognizable in terms of lots of code that's the same, at least in terms of the type of code, compared to the one that we've been using previously in class. One thing that's different about this model is at the very top here, you can see it's got these smooth sphere half space force defined. What is that exactly? That is, if I go back to, I think I closed it. Shoot. Let me see if I can pull it up in OpenSim here. I closed my visualizer. Let's just see what it looks like if I open that model in the GUI here. He's in the floor. Let's move him up a little bit. There we go. Okay. So that part in the code that says, smooth sphere half space force, and there's one that's called contact heel L and contact heel R and contact front R, contact, what's all that? That is those blue shapes down there on the foot. I'm gonna zoom in there. It's defining points of possible contact between the foot and the ground. And these are contact spheres or contact geometries. We'll talk more about these in a little bit further detail in an in-person class. It's difficult to explain the mechanics here virtually over a computer. But picture this model moving in a way that kind of presses it into the ground here. And so here, for example, that sphere on the toes would be, pressed fully under the ground, and that one on the heels would be about halfway into the ground, right? You could also think of this as being like a squishy, deformable part of the body that's then squished or deformed by, about that distance there. And based on how much it's deformed, it would push back with a certain force according to Newton's laws of reaction there. And so that contact sphere on the heel, and also that one on the toe, if you go into the code here, it's got a stiffness defined for it and a damping or a dissipation defined for it. The stiffness there will affect how much force it pushes back with when it's deformed by a certain amount. The dissipation will affect, how much the force is dampened out by when you deform it fast. And then you can define some different friction coefficients here, which will affect the frictional forces that contact sphere produces. And so defining those contact points on the foot, that's in a nutshell how the model generates its ground reaction forces. Okay, and that's kind of the fundamental difference between this approach to simulating or analyzing human movement, and the inverse dynamics approach that we've been talking about, earlier so far in class. With the inverse dynamics approach, I took measured ground reaction forces and I imposed them on the model. I didn't have to worry about, modeling mechanistically, like the mechanics of how the foot interacts with the ground to produce those forces. I didn't have to come up with like, a stiffness of the foot and the geometry of foot ground contact. This is a very simple geometric model here. This says you have this little sphere here, and that's where your forefoot can contact the ground, and you got this big one here, that's where your heel can contact the ground. But you could picture like an array of smaller shapes over the bottom of the foot there, representing a more complicated foot ground geometry for a more complicated foot. For inverse dynamics, I didn't have to come up with any of that because I had measurements of the force on the foot and where it's applied on the foot. I could just impose that on the model. But remember that imposition of that force on the model that the model didn't create, that was the origin of those residual forces, right? If you look through this code, you will see that there's no residual actuators, or none of those reserve actuators. None of that is necessary in these forward dynamic simulations. It always automatically has to obey laws of physics. So the reason it doesn't have any residuals, whereas the inverse dynamics approach had those large residuals, is because here in this optimal control approach, we're not imposing a specified ground reaction force in the model. We're giving it a target force that we took from measurements, the same general origin of forces that we used in inverse dynamics, measurements of human ground reaction forces. But we're not requiring it to use exactly those forces. We're asking it, try to track these forces as close as you can. And so I'll go back to my, example, older simulation here, where you can see down here in these black forces on the left, that's my able-bodied model trying to track able-bodied ground reaction forces. And it does it pretty well. But if you compared that, graphically to the actual mean average values of the human experimental ground reaction forces, it wouldn't be spot on. Like that black line, the simulations forces would not be exactly on top of the measured mean ground reaction forces. It deviates from them a little bit, or it doesn't track those motions perfectly. And same thing for these joint angles. The model tries to track those as close as possible. Hopefully it gets reasonably close to them, but it's not required to move exactly as the prescribed motion is moving. Okay. So that's kind of the fundamental difference, or one of the fundamental differences between the inverse dynamics approach and the forward dynamics approach. I think of it as like a hide the error question, or like, where do you want the error to be? There's always going to be an error. You can pick where is it and what is its form, but there's always one. In inverse dynamics, the error is I have these fictitious, hand of God was the term one of the papers used, but these fictitious forces on the pelvis that are fictitious in the sense that they're not really there when a real person is moving. When a real person is moving, it doesn't have those residual forces on the pelvis. We had to add them to explain the unexplainable, to get the laws of physics to balance out, because I'm requiring this model to produce these ground reaction forces that it didn't produce, right? In the forward dynamics approach, I lift that requirement. I say you can produce whatever ground reaction forces you want that are consistent with your physics. In fact, your ground reaction forces have to be consistent with your physics because you yourself, the model, are producing them. Okay? The error comes in the form of, now I don't have perfect tracking of the motion and perfect tracking of the ground reaction forces. That deviates a little bit. Okay? So that's the main thing in this code that is different, or that is not present in the more complicated, more detailed model that we've been using here for inverse dynamics. If you wanted to do like a simulation in Moco with a model like this very complicated, high-dimensional, many muscles model that we've been using earlier in class, you can easily do that. Not easily in terms of time, but the way that you would do that is not fundamentally different from the way that we did this simpler simulation here. It wouldn't be quite, you'd have to modify the code quite a bit. It's not as simple as you know, taking, where is it here? If I go back to my OpenSim folder, it's not quite as simple as, you know, taking the 2D gate model here and swapping it out for the Rajagopal model and then just click run and it works. But it's not dramatically more complicated than that either. You got to change a few things in the code here, but modifying this to use a much fancier, much more detailed model is fairly straightforward to do. And that's the real benefit that doing these types of things in OpenSim has allowed. Back when I was a student, advancing something like that from a simple 2D example to a large scale, you know, realistic 3D model would have been months, maybe years of work. Now in OpenSim, if you know what you're doing, you can do that in maybe not minutes, but a motivated and well-trained person can do it in a couple hours. It's not a large undertaking for a lot of people. Okay, let's step through some pieces of this code so that we can hopefully understand a little bit better how it works, because we'll be playing around with this quite a bit for the rest of class. This example right here, and here I made kind of a truncated version of the actual examples code here. I chopped out everything below this part that says extract ground reaction forces. I deleted everything after that so that it only does this tracking problem here. And so that's about 200 lines of code there, fairly short on the scope of MATLAB codes. If you look at the code that I use to generate my pretty complicated Moco simulations these days, it's like thousands and thousands of lines of code. I started from this exact code here and then gradually added complexity to it and features to it and bells and whistles to it one piece at a time. And I can't stress enough how important that gradual iterative process is to learning how to do this really well and to understanding how it works and getting it to work well. If you sit down and just from scratch start with like the most complicated model that you want to possibly use and try to generate a simulation with that, it's probably not going to work. It's a lot better to start from a simple example like this that works, and then gradually make small additions, small changes to it each time, rerunning it, confirming that it works, and then using that new, confirmed, slightly more advanced result as the starting points for an even more advanced one, and then a little more, and then a little more, and a little more. That iterative process here is really, really important to follow. So let's just end here by stepping through this code and trying to get a better understanding of exactly what's going on here. And this has pretty detailed comments here, so definitely read through the comments there. They're pretty helpful. This was written by my friend and mentor and colleague Brian Umberger, who's probably one of the best persons in the world at doing these types of simulations and these methods. So this is a really nice resource here. This example that he provided for the community here. So Moco has a number of different kind of, I'll say like prefabricated types of problems you can tell it that you're trying to run. These tracking problems, these problems where you're trying to track a target data set as well as possible, typically with some constraint or limit on the amount of muscular effort you want to use to do that, is a really common problem that people do in biomechanics. And so that's Moco track. It's kind of a built-in approach to setting up a problem to do that general type of simulation. So that's what they're setting up here. So they start by just defining that Moco track problem, and then they set a name for it that'll be used for labeling and stuff later on. And then down here, he's setting some weights for terms that he's going to put into his cost function a little bit later. These parts down here, this business where it says table processor, for that, he's reading in his data file that has his reference coordinates in it. And what were reference coordinates? That was this file here that has the target motions in it. So this is the file that has, as functions of time, the movement data for how we want the model to ideally move. So the target values of its motions for the pelvis and the hip and the knee and the ankle and whatever other coordinates are in the model that we want to get to try to track some particular motion. And so when I started working with this code, This was actually the first change that I made. I had my own experimental data values for these motions here, for like angle of the pelvis, angle of the hip, angle of the knee, all these things in here. And so that was actually the first thing I did, is I took this file and I replaced it with my own experimental data values to then rerun it and get a simulation that tracks my experimental data. You probably saw when we ran this that when it finished and animated itself, it was kind of this strange looking, kind of herky-jerky walking motion. I think it was tracking like a result of like a predictive, like minimum energy expenditure simulation from that model. I don't think it was I don't think those reference coordinates in this file here are actual like human experimental walking data. I think it's like results from some other simulation. And so that was the first thing I did, was just swap out these numbers here for my own mean experimental data values and run the simulation and try to get it to work with tracking like real human experimental data. But if you wanted to do that, it would be as simple as creating a new file there, putting in your measured values here for those motions, and then referencing that file here instead. Okay. I'm not going to go through all this one line at a time. A lot of these are just different settings here, but like, most of this you would just leave the same. But like, for example, if your stride duration here in your experimental data was presumably a different number, a different value than they had specified here, this is where you would set that, right? So here, their stride in their reference coordinates there was about 0.47 seconds long. And in your measured data, if you were going to put your own data in there, it'd probably be some different value. So you would change that down there. Okay, Moco has a number of goals that you can get it to pay attention to when it's doing its optimizations, when it's finding the values of the muscle controls that minimize that cost function that you specify. This one here is what it calls a symmetry goal. This is a goal that says, I want you to perform a periodic motion. I want you to move in a way that you start in the same, or you end up in the same pose that you started at, right? Another way of thinking about it is you can say you take your model, and let me just put it in like some approximately, heel strike position here. So something like that, right? And it would be saying, okay, you started in this position. After that 0.4 seconds, where you're probably over here, you have to end up back in that same position. Okay. The symmetry thing comes into play in that, because this is a simulation of able-bodied walking, which is presumably, bilaterally symmetric, like the step of the right leg and the step of the left leg are probably more or less identical, just, shifted 50% and mirrored. If you can get away with that, like if you're simulating just straight up able-bodied symmetric walking, then you don't need to simulate an entire stride of data. You can get away with simulating a step of data. So then how do I reconstruct a full stride from that? Anybody have any intuitive, brilliant guesses there? If all I have is one step, say the step of the right leg, how do I reconstruct that into two steps, the right leg and the left leg? It's a tough one. Could I copy and flip it? If I'm okay with assuming it's symmetric, that should work, right? So what my right leg is doing for the first half of the gait cycle, my left leg at that same period of time, so picture like my right leg doing its step, the step that involves the right leg on the ground. While you're doing that, the left leg is not just sitting there doing nothing, right? The left leg is going through the second half of its gait cycle, right? So if I end here after one step, I can, in my results, in my data of my simulation, represent a full stride by taking my result from my left leg for that first step, flipping it and tacking it on to the end of my right leg. Okay. And then I do the same thing for my left leg. I take my result from my right leg, I mirror it and tack it on to the end of my left leg. Right. It's not real obvious that that's what's happening here in the code, unless you know that's what's happening. But all this business down here where it's talking about symmetry and symmetric muscle activations and all that stuff, that's what that is doing there. It's assuming that you do one step, and then from that, I'm assuming it's a full symmetric stride and reconstructing that full stride from just data of one step by basically mirroring the left and the right leg and then stitching them together into 2 full steps. I've personally never done that. I've always just straight up simulated a full stride and not done any of this. One, because it makes specifying this symmetry goal a lot more straightforward. It's a lot easier to say, okay, if your left knee starts at this angle, at the end of a full stride, it's got to end up back at that same angle, right? You don't have to worry about, comparing the left knee at the start of it to the right knee in the middle of it and all that business. You can just get away with saying, okay, start and stop in this same kinematic state. So defining it gets a lot more straightforward. If you're simulating a motion that's going to be asymmetric, you also just can't assume this symmetry, this reconstruction of a full stride from a single step then doesn't hold water. It doesn't work. And I've always been doing these simulations with the purpose of eventually simulating asymmetric gait, people with prosthetic limbs. And so I've never bothered with the symmetry thing. It's a good thing to do in terms of time saving if you are only simulating like able-bodied locomotion. But if you're okay with the simulation is taking a little bit longer, then I think it's probably something to skip a lot of the time. But that's what this part of the code is doing, is it's defining that symmetry constraint, allowing you to reconstruct a full stride from data for a single step. This part is also doing that for the muscle activations. Those should be periodic and symmetric. It doesn't have any upper body muscles. It's got this nebulous like torque generator at the lumbar joint that controls like the pitch of the trunk there, and so that's a symmetry constraint on that.
Your screen is not shared.
Oh, sorry. So the symmetry part there for the muscle activations, again, it's the same thing as what it is for the like the angles and the velocities and things like that, trying to get those to be symmetric and periodic. Next part down here is specifying that weight on the control effort, which is their term for the muscular effort. Unless you go in and tell Moco to do something, it's going to try to minimize the sum of the squared muscle excitations. And then here you're specifying that weight from back up here at the top on that muscular effort. So if I wanted to, for example, generate a simulation that cared less about tracking experimental data and more about minimizing muscular effort, I might make this 10, 100 or something like that. If I wanted the model to pay more attention to tracking accuracy, and regardless of how much effort it took, then I might reduce that to 1 or to 5 or something like that. Down here is where it's defining tracking of the ground reaction forces. This is not the best way to do this. It's tracking the overall magnitude, not the magnitude in each direction, but it's a fairly easy change to get it to track each vector in each direction if you want to do that. Here under bounds, to do this optimization, you need to give it a range of values that it can possibly choose for each of the kinematic states of the model. So you have to tell it, what's the range of values of pelvic tilt angles that you want me to choose between. Same thing for the, other, pelvis XY coordinates, hip angles, knee angles, all these things. You have to give it a range for each one that you want it to, to choose values within that range. This is important to pay some attention to. The wider you make these, the harder it's going to be to find good solutions. But the more narrow you make them, the kind of easier it's going to be to find good solutions. But you don't want to make them too narrow, right? Like you might think, oh, I want to make these to be as narrow as possible so that it, you know, quickly hones in on a good result. That's not really how it works. You have to give it, you know, some bounds to be able to kind of explore the solution space and find good values for. So don't make these like infinite, but don't make them too super narrow either.
I had a question.
Yep.
Sorry.
Yep.
How do you decide, like, if you didn't have this reference code, how do you decide what these bounds should be?
I generally base it on like the movement that I'm doing. Like for the knee here, you can see that it's saying the smallest value you can pick is -50 degrees, which would be flexion, and the biggest value you could pick is 0, which would be full extension. If I was going to simulate running, would that be a good idea? Is 50 degrees of knee flexion enough for realistic running? It's pretty flat, right? So for running, I might go in and make that, you know, 100 or something like that. So I base it on like the movement that I'm doing. So like typically, let me pull up my get my paper back here. Like here, I might look at this and I might say, okay, in my experimental data, you know, I do not want to let it hyperextend its knee. I'm just going to say you can pick an angle of 0, no bigger. But then in the other direction, I might say, oh, you can go as big as 75 degrees, right? That would give me like, you know, a range of within, you know, 2 standard deviations of the most extreme knee flexion angle there or something like that. So I'll typically base it on looking at the experimental data for the movement that I'm doing. $50 here seems kind of low even for walking, but Brian picked it and it worked pretty well, so I didn't change it. Okay, then that is all set up, and then this little one down here just gets it to run the problem, and then it'll chug away for a while, and the rest of this is outputting data to files. I was mentioning to Sam during the break, always set these up so that when it's finished, it writes the result that you want to output from it to data files somewhere. I've had it'll often like print onto the screen. I don't know if you can see this here. Yeah, it'll print onto the screen here like some values of stuff for results. I'll often have it like right to the screen, like in text, like what the metabolic cost was and things like that. Don't get into a situation where you're like, you know, coming back to look at that and then like manually typing it in or writing it down and recording it somewhere. I've many times had a simulation finish, and because these take so long, I'm not there to like monitor it when it finishes, and then the power goes out or the computer crashes or whatever, and I've lost 3 days of work because I wasn't there to, you know, to write down the result that I was waiting for 3 days. So always set it up to write the result to a file so that you can go back and pull it back up later. May seem like silly advice, but a lot of people skip that part and waste a lot of time by having to rerun simulations that they already ran. For this particular type of optimization, there's no element of like randomness to it. Like if you ran this same code again here with no changes, you would get exactly the same result. There would be literally no difference to it. It would be down to, you know, double precision decimal places, exactly the same result. There's no element of randomness or variability to it. There are some optimization routines that kind of search randomly around the solution domain, and those will get a slightly different result every time. But this one is a gradient based, which means it always gets the same result every time. So if you get a bad result, running the same code again will get that exact same bad result. Nothing will change. Okay, a lot of this probably a little unclear since we haven't actually dug our hands into doing anything with it yet, but I wanted to just give kind of a quick introduction of it here before we dig into doing some more practical things with this particular example in the future. That is all I wanted to cover, and about all the voice that I've got with my recovery here. But any questions, anybody, before we close things off for today?
I have a quick question.
Yeah.
The screen you just showed that had the solution on it that when you ran it, it came up with.
Yep.
What exactly is that solution saying? I didn't really, I was looking at it, but I don't really understand what it's telling me.
So most of that is just optimization algorithm jibber jatter. There's not too much that is relevant to us in there. So like there's a little bit that's useful. So like T proc here, this total at the bottom, that's the total amount of seconds that the optimization took combined across all the cores in my processor here. T wall, you can see that's a shorter amount of time, 60 seconds versus 278 seconds. T wall is the time on a clock on the wall while this was running. And you take that times however many processors it's running on, and that's, you know, the total processor time that it took, right? Those are often things that people will report for like numbers for like efficiency or like how long the simulation took and things like that. But T wall here is like the amount of time on a clock on the wall that surpassed or that elapsed while this was running. The rest of this is often not terribly useful to us. Unless you're like really deep into like the minutia of, you know, optimal control methods. The one thing that is valuable here is while it was running, you see these numbers like getting printed out like line by line to the screen there. Each one of these is like the model's current result for this simulation. So you can think of this as each time it's doing an iteration here, that's the model trying a different possible set of muscle excitations and muscle states to try to minimize this cost function while satisfying these constraints. We'll talk a little bit more in detail in an in-person class about what this algorithm is actually doing, this direct collocation method, but I didn't want to try to explain that virtually here today. The numbers that you want to pay attention to here, this first one is the value of like your cost function. And this is a good thing to use to set up your cost function in a way that you can look at this and kind of get some intuition on like what's a good result. And this is why I like casting things as like being scaled by standard deviations, because then I could look at this and I could say, okay, if I get a result here of like 1, meaning it's tracking my experimental data to within 1 standard deviation on average, that's pretty good. If I get a result here of 10, that's really bad, right? Tracking something to an average of 10 standard deviations away from the mean, that's really bad, right? But this is the value of the cost function that it's currently at and that it eventually settles on down here at the bottom. This inf PR, it's not exactly the largest constraint violation, but it's something related to that. A constraint violation is something like somewhere in here in the code, it specifies that the model has to walk at a certain average speed. You might specify, you know, 1.2 meters per second or something like that. And that constraint there would be like, you know, okay, it's walking at, you know, 1.2 meters per second plus, you know, 5.78 times 10 to the negative 3rd meters per second, right? Or it's also like in here is the violations of the model's physics, you know, F equals ma down to an error of, you know, 4.49 times 10 to the negative 6th newtons or whatever, right? So ideally we want this number to be really small, right? That should be far smaller than 1 a lot of the time, because that's the violations of the constraints that I'm giving to the simulation for the result to be good or to count. The other number here, and the one that I actually pay the most attention to, is this column with this 1 decimal place number in it called log mu. I have no idea what this actually is, but it's a good index of, is this a simulation that I should let continue for a few days because it's probably eventually going to converge on a good result? Or is it something where there's some problem in my code or my setup and I just need to stop it and not waste my time letting it go for 3 days? It'll typically start at 0, and then it should eventually pretty quickly, and here it happened after 37 iterations, should pretty quickly go to a negative number and then should keep getting eventually progressively more negative. Okay. And you can see there, that's generally what's happening here. If that fairly quickly goes negative and then largely stays negative, that's a good sign that this is going to converge on a pretty quality solution. I don't know why technically that's the case. That's just been my observation from doing this for a few years. And I've had other people that know more about the technical specifics of optimal control than me say that's a thing that people monitor. Like if this log mu goes negative and stays substantially negative and gets more and more negative, that means the algorithm is honing in on an optimal solution. If it doesn't do that, then, you know, like if you got through 200 iterations here and it was a value of like +8, that's probably one that you should just stop and try something, you know, try a different initial guess or try a, you know, different model or something. You know, something's wrong if it's not quickly going negative and staying negative. So that's probably the most important thing to pay attention to here. One other real important thing I forgot to do, I'm going to start this again. Oh, you guys can't, yeah, you can see my screen. Okay. Okay, so it's running here. This only takes a few minutes, but suppose it was going to take like 6 days and I realized, oh shoot, there's a problem. How do I stop it? Oh, you go to MATLAB and you do, you know, period, you know, command period or option C or control C or whatever. It doesn't work. For whatever reason, this optimization thing overrides MATLAB's normal like force quit thing. You can't make it stop. And so first I was like, oh, this is a big problem, guys. I can't, you know, let this run for 3 days. It's going to burn up my computer. See this little file up here that it created? Delete this to stop. That's literally, you know, that's giving you the instruction, delete this to stop. So if you right click on it and delete it, then it stops. So that's how you terminate it if you want it to kill what it's doing there and not just go to completion when it may actually never complete if you just don't have a good thing, something that's going to hone in on an optimal solution there. Okay, other questions? All right, we will see you next time. Have a good weekend, y'all.